All right, so we started with this expansion of the Hamiltonian, the wave function, and the energies in this Taylor series, where we have the individual derivatives, and we did so starting from some coupling parameter lambda. So that was the idea, what we did yesterday. And then we have seen that if you insert this expanded expression in the wave function, in Schrödinger's equation, then what you end up with are these individual expressions for the nth order perturbation. There's something in the chat. Can't hear me.
I can hear you. I think it might just be you, Julian. Don't know.
All right. So in all these cases, we have now individual expressions for the perturbation up to nth order. We have seen that you can gradually solve them by starting with the 0th order expression, which is the Schrödinger equation for the unperturbed system, so the one for which you already have a solution. And then you can gradually solve this by always inserting this into the next one. So you solve the 0th order, you insert the result into the 1st order, and then you solve for 1st order and insert this subsequently. So that's the individual idea. Now we started looking at some number example, and we insert this, for example, for the 1D anharmonic oscillator, and we saw that this allows us to get some corrections for the individual energies. Now let's continue here. Switch this. All right, so we did look at this number example, but we started for this for the case here, where we looked at its 0th order, 1st order perturbation one for the case of the two numbers n and m being the same. Now, obviously, the next step is to have a look at what happens if they are different. So can we get some information based on that? So we had the case for 1st order perturbation. And now we're going to look at n not equal to m. And we have this expression, I'm just copying this from above so that you see it once again. We have this expression En of the m of the unperturbed system minus En of the unperturbed system. And then this is psi m of the unperturbed system ket psi n of the perturbed configuration. And that was equal to En of the perturbed system. And we had this Kronecker delta Mn minus psi m the unperturbed system with, so the expectation value of that one, but here it's psi n, so of the perturbed Hamiltonian with psi m, so with the psi n and n for the unperturbed system. Now, we're explicitly looking at the case of n not equal m. So that means that this term here needs to be 0 because of the Kronecker delta. And we know that this one here has to be not equal to 0 because we mandated implicitly early on that we don't want to have degenerate configurations. So I will write this here, no degeneracy. So in this case, now we, in order to move this along, the idea is we want to see what can we extract from this expression if we consider the unperturbed basis only, so the unperturbed size, And the reason for that is, of course, you have them. So in the perturbation approach, this is information that's basically it's there already, is money on the table. So can we use that in order to express the perturbed wave functions psi n from the unperturbed ones? That's the goal now that we're working towards. All right, now the problem is that right now we have this mixture of everything, right? So we have the perturbed Hamiltonian, which is something we know in principle, but we have psi n only as part of the expression, but we don't have this isolated, and we would like to have that. So the way to do that is to say we expand psi n1 in the basis of psi n0. So we're trying to find some expression that gives us psi n1, which is this part here, but to express it in the unperturbed configuration. Now, you know from earlier chapters how projection works. So the idea is to say that psi n1 shall be the infinite sum from m is 1 of some projection coefficient, amn, times the unperturbed basis. Now, so far no magic happened, because this you can do with any complete basis. So it's an infinite sum, so it's complete, which means that any set of linear independent basis functions should be able to be converted into any other. Now, these coefficients, a, m, n, they are the integral of the two functions involved. So it's think of it as the projection of one basis vector into the, depending on the projection of one basis vector onto any other basis vector of this new basis set. So from that perspective, that's a plain simple projection. There's no requirement, except for both bases being complete, and there's no requirement for this to work. Now, but now we see that this thing over here is precisely this thing. Those two expressions are the same. So let's insert that and see what we get. So if we do that, then insert, then what we get is En, the unperturbed system, minus En of the unperturbed system, times ANM. Sorry, that's wrong. AMN. And on the other side, the first term was 0, so we're only left with the bracket, the expectation value there, so that would be psi n0, perturbed Hamiltonian, and psi n0. Okay, so now we have these individual expressions, but they are valid for every n and m. So now we can reorder this we can solve for AMN, we can solve for this one here, and consequently then insert this into this expression, what we had. So that's the idea. So that means what we get is psi n1 is now the sum over the infinite sum over all those basis functions, and we have psi m0 and psi n0. So that's what we had on the right hand side, divided by, now I'm swallowing the minus into rearranging these two, minus En0. And that, of course, now times y psi n0. And this is wonderful, because on the left side, we have the perturbed wave function. And on the right-hand side, we have the unperturbed energies and wave functions for our, just applied together with our perturbed Hamiltonian, which is part of the problem description. So that one we know. From that perspective, this is beautifully convenient. You can basically reuse whatever information we have. And before that, you might remember we had this definition defining our matrix element of the perturbation. We do the same thing here. So the 3 bars mean defined as, so that would be m is 1 to infinity over mn, that is minus mn0 psi n. So this allows us to introduce these two terms here, and they are what's defined. So maybe we do it like this, so it becomes clear. So this now gives us a way to get the perturbed wave function just from the perturbation outside. And you might ask, so from the unperturbed system alone. Now you might ask, so what if we have n and m being the same in this picture? It's a summation over all m's. So this n is bound to appear. But we have seen, we have shown earlier we have shown that for the case m equals n, we have a n n, which by the definition that we have here would be psi n unperturbed, psi n perturbed, and we have shown that this is 0. So from that perspective, this means one of the terms in the sum is 0. All right, now this is beautiful because this means that for first order, we only need information about the character of the perturbation, that's the change in Hamiltonian, and about the unperturbed system. That's awesome. Can we do this for the second order as well? I mean, the more orders we can do this with, the more accurate we can get in this perturbative approach at limited extra cost, because we already have all these unperturbed informations. So let's see about that. So was first order. The hobbits would ask, what about second order? So we say second order case. And remember, we had this thing earlier where we collect the terms based on their order and lambda. And that's again where we start off. So from the second order term, I will just copy it over so you see it clearly. So that was the unperturbed Hamiltonian minus the unperturbed energy times, keep in mind, we always need so the second perturbation of the wave function. Keep in mind, in every term, we need to be quadratic in lambda. That's why we have 0th order, second order here. And now we get the case where the second order is in the energies and the Hamiltonian. Then, of course, this means that we need the unperturbed wave function for that. Now, the last thing is only the mixture, where both factors are linear in lambda. So that would be the first order minus the first order of the Hamiltonian times psi n, the first perturbation. So that's the same thing as you had above. So as above. Now we do exactly the same thing as before. Remember, before we did this projection onto psi m0, and now we do the same thing. So we do again this psi m0 projection. Okay, so this means basically left multiplying psi m. So we get psi m0 times our unperturbed Hamiltonian times psi m2. That's the first term. Minus en0. It's a scalar value, so we can just pull it in front. So that would be psi m0 psi n second order. So that was the left part, and that's equal to en to second order. It's again a scalar value, so it can be pulled in front, psi m0, because that's what we project on. And then the first one is psi n0 to add. And then minus again psi n0. Now we have the operator, second perturbing operator, second order perturbing operator, the Hamiltonian times the unperturbed wave function plus first order energy, again a scalar value, putting it in front, psi 0 and psi n, the first perturbation. And then the last term that we have is psi m0 with the first order perturbing Hamiltonian times psi n1. So those are all the terms. And now there's a few things to keep in mind. So the first one we know is this one here. They are of same order. And this means, so the same perturbing order. So this means they need to be the Kronecker delta nm. And here on the left part, we have the Hamiltonian together with the zeroth order perturbing function, which means that this is an eigenfunction of the Hamiltonian operator, which means we can pull the corresponding energy out. So this is equal to em0 of psi m0 psi n to second order. So if we use that, then we can say this is now, we can group terms, because now we have in this one here and this one, they are the same. So this can be grouped. So let's do that so it becomes clearer. So we have em0 minus en0 times psi m, so the unperturbed psi n, the second order perturbed psi n. That's what we had on the left side. And now we can shorten the right-hand side a little bit by saying this is the Kronecker delta plus n1 of psi m0 psi n1. And then we have the two expressions from the Hamiltonian with the operators. So that would be then minus psi m0 second order perturbation. That's just copying the terms that we had in the previous line. They are unchanged. So first order perturbing Hamiltonian of psi n1. Okay. Doesn't look too bad. Now let's look at the case. What happens if m is n? They're the same. Case m is n. And in this case, we now have two things. We know that, so let's maybe do this in green, case n is n. We know that this expression here needs to be 0. We've shown that earlier. And we also know that this expression here needs to be 0. Sorry. So that means we can, we also know that this Kronecker delta, of course, that this is 1. Huh? So if we do that, then we can rearrange things so that we can get an expression of en squared. So the left-hand side is 0, and this is the second term on the right falls out. So we can just solve this for en squared. And so a square second order perturbation. And this is then psi n unperturbed times second order perturbed Hamiltonian times psi n unperturbed. And you already see where this is going. Plus psi n unperturbed times Hamiltonian, perturbing Hamiltonian times psi n 1. Now you say, okay, that doesn't look too bad, right? We have the energy on the left-hand side. We have the something which is again a function of our unperturbed system in the first term, and the Hamiltonian, the perturbing Hamiltonian that we know. And on the right-hand side, we have something from the unperturbed system, great. Something we know, awesome. And then something of the perturbed system. But there's a good news. We've just shown, just earlier today, we have shown that we can get those things by the perturbation, right? So maybe it's a good idea to highlight this so you keep in mind that this is an important aspect. So here we found a way to express psi n1, so the perturbed functions. We found a way to express that based on unperturbed information and the perturbing Hamiltonian as we know it. Which means that implicitly, this already is an expression based on something that is only either the unperturbed configuration or the perturbing Hamiltonian, both things we assume to be known. So in maybe to set things into perspective, this is also the Hellman-Feynman term for second order. And if you were to use linear perturbations, then of course this would cancel out. So in practice, often you have linear perturbations, and then of course this thing would be 0. Okay, now I promised to show this explicitly, how we can get this into something which only depends on stuff we know. So let's do that. Recall that we had this expression for the perturbed wave function, which was m1 to infinity of hmn perturbed divided by minus emn 0. psi n 0. So that was what we had earlier today. Now we can insert this, and what we get is En second order is this infinite sum HMN first perturbation minus EM 0, and then psi n 0 times the linear perturbation times psi n 0, and this we had defined as 1 in n. Right, so this means here we have again the expression for the perturbed energy only in aspects of either the perturbing Hamiltonian or in terms of the unperturbed basis functions. And that's really neat, because in this case what we get is something only in those expressed as the energy expressed only in information that we already have at hand. Now you can see that we have, sorry, this is Mn, correct this, like so. Now there is, now we have the same term twice, or at least something very close to it. We have HMN and HNM, which only differ in the ordering of prime ket, but since neither of them is an eigenfunction of the perturbing Hamiltonian, we have to work a little bit in order to show that this can be further simplified. So ideally, we want that in the perturbation, our eigenvalues still remain real, and they should, because you can define the Hamiltonian that goes with it, and that would mandate that for the perturbed system there should be real eigenvalues. So let's have a look at this product here, namely the product of this part and this part, and let's look at that one in particular. So that would be HMN, that's the one in the fraction, times HNM, both up to the first perturbation. Those were the two we have defined. Now this is exactly psi m 0 with the first perturbing Hamiltonian. Now we have the same thing, just with an inverted order of our brass and kets. Now, we know that we can rearrange things. We can flip the order of bra and ket if we take the complex conjugate. That's universally true. So let's keep the first one as is, and let's flip the second one around. And now and this is the complex conjugate. Now, the nice thing is the product of these two is exactly the norm of one of those expressions. That's just by definition of a complex number. so the norm squared. That, of course, means this would be HMN first perturbation squared. That allows us to simplify matters. So now we get in second order is the sum, so it's basically this expression that we had above in the box, this infinite order summation of HMN squared divided by ENN0 minus that, so that's the same. Now this is crazy, because this is only a function of the unperturbed energies and the unperturbed, use N, and the unperturbed wave functions. So this is a crucial result, because in principle this means that if you have your perturbation, if you have your unperturbed configuration, then all the information in principle is there. And you can kind of guess, because you have this concept of always using the perturbed wave functions from one order below. You can kind of guess that this carries over. You can extend this to the third order, but we're not going to do it here. So can be extended in spirit. That's the point, right? In spirit to the third order. And this is a really, really a crucial thing, because now this tells you something about the reuse of information. If you already know your reference system well enough, then this carries over to knowing approximations of perturbed systems. Now, it's no free lunch, right? It's still part of a Taylor expansion. So what you get is something which is approximately getting you there. Sorry. Which approximately is getting you there, but it's not going to be perfect. It's not exactly the same as if you were to solve your target system again. But keep in mind that this way, the one case that you already have allows you to look at a larger set of perturbed configurations without having to redo each and every of those, just because you already have this information. So let's insert that into our Taylor function. The Taylor expansion that we had before. And so we have that the energy to nth order was the energy of the unperturbed system plus the first order contribution of this Hamiltonian, plus now the 1/2 comes from the fact that this is the prefactor in the Taylor series. So that would be the infinite sum from 1 to infinity of HMN1 squared over minus EMN plus all the higher order terms. So typically speaking, what you would do is you would say, all right, maybe second order already is pretty good. And how about we stop there? So then what you get is, if you were to do this, then you have En is roughly this part here. That means you have the 0th order approximation, the first order approximation, and the second one. And all of that exactly in a pen and paper derivation only requires the unperturbed configuration, to know the unperturbed case and your perturbing Hamiltonian. So that's I think the core reason why this perturbation theory approach is so powerful, because not only it allows you to express the energy of some target case in something that you can calculate, but it also allows you to reuse the information of your reference case, because otherwise it would have no advantage of using this perturbative approach if you weren't able to get things back onto this reference case that you already have. So technically speaking, you can imagine, if I know one molecule, one configuration good enough, then now I can apply some, say, external electric field, and I can perturb the electronic structure of this molecule. But of course, I can change the way my external field looks like. So you could say, what happens if I apply a field in this direction, in that direction? There's many external fields that you could apply. And then a perturbative approach would allow you to reuse only the information of the unperturbed reference system to exactly recover the corresponding energies. This, of course, is only approximate, but usually, and this is often seen in practice, the first few orders do carry the most explanatory value, that then later on allows you to simplify matters and don't do as many calculations to at least get a very good understanding of this local vicinity of chemical space. So let's sum this up, wrap this up. So we have our cases summary. So we have those cases where we have the wave function on its own, and of the Taylor expanded wave function, and we say we want to approximate this by the wave function of the unperturbed system plus the sum over n equals n, unequal n, of this perturbing Hamiltonian elements that we defined earlier on. So that's very much the same as we had before. So we expand this in the corresponding order, plus higher order terms. And now there's a little bit of a caveat here to keep in mind. This thing might change sign. So that becomes most important if the energies are close to each other. So if in the spectrum you have not things which are exactly degenerate, because we excluded that, but where these two are actually very close by. So this means for important for small energy differences. And now, in this case, what we see is that the moment you look at those perturbations, so that was one thing. The moment you look at those perturbations, then there is a relation between energy contributions and the matrix element part of the perturbing Hamiltonian. And we have seen that the second order energy contribution is just a function of these perturbing elements. So that's just a function of the perturbing Hamiltonian elements and of the corresponding energies, the unperturbed system. And that's the crucial part, that it's always the information about the unperturbed system that goes into the second order perturbation. Now, it's also important to keep in mind that in all we discussed in that regard was for non-degenerate cases. There is an extension of that logic. So for degeneracy, once you can have these the energy differences, or once you can have the energy differences between two levels be the same, so the difference be zero, then the response of different levels can go in different directions, and you need to treat this explicitly. So if you have degeneracy, then you need to take this into account explicitly. We didn't look into that so far. We have also seen that in this expansion picture, every order of expanded wave function forms a complete basis. So every order of psi n, say k, forms complete basis. So you can project those individual components. From there, you always keep the full information, which is required, because then remember when we used in the second derivation of the second order terms, where we used the fact that we already have the perturbed functions from the first order perturbation. This thing would only be possible, the reuse of that is only possible if in every order you effectively keep your individual, keep the completeness of the basis functions. Otherwise, this projection would be incomplete, and then you have no strict equivalency. So I think the key takeaway here is that perturbation theory gives you one way of reusing information. You do have your unperturbed system that might be easier to solve, and now you find a way to take that information and transform it onto some new system without having to redo everything from scratch. Of course, you still have to do something, but at least to get an approximative answer for your target system at typically a reasonable accuracy, exactly from this perturbative approach. And the core idea on how you get there, and to keep in mind how this has been developed, is you start from Schrödinger's equation, and every element you Taylor expand, and then you collect terms in order of lambda. That's maybe the key takeaway. If you can keep that in mind, then we did something in the past 2 days. With that, I don't see any questions in the chat. If you have any, let me know. Otherwise, thank you very much and have a good day.
I do have a question, actually. When you mentioned when m equals n and then amn equals, you said it was shown earlier, but I think I missed where that was shown.
That was here. Yes, shown earlier. This one, you mean? Is that correct?
Yeah, that is 0.
Yeah, there was the overlap between the perturbed and unperturbed. The first order perturbed wave function and then unperturbed one. I think we did that yesterday. Let me find where it is. I think it was before this. Here it is. So this part here, that's the expression. So how we got there was we started from the fact that this Taylor expanded wave function should be normalized. And then we expanded each of those infinite sums to first order. That's why we get these two expressions here. We collected terms, neglecting anything which is square, second order, and lambda. And then we use that the unperturbed wave function already normalized to end up with an expression showing that then this overlap needs to be 0.
Okay, thank you.
All right. Any other questions? All right, then thank you very much. I'm